Hello everyone, in this video we're going to talk about logic gates. Now you may or may not be familiar with logic gates, you may have heard them in the past but you don't really know what they are. So in this video we're going to cover three different types of logic gates. We're going to cover the NOT gate, the OR gate and the AND gate. There is some other gates out there but for this course they're not relevant and we don't need to know them. We've got three different types. Our NOT is represented by a symbol like this, so it looks like an arrow on its side with a circle at the top. Then our OR looks a little bit like a spaceship or a out of shape D, and our AND logic gate looks like a D. So you might be thinking, what exactly does a gate do? So similar to real life, a gate stops something from entering. So we might use a gate to stop somebody entering our property, or we might leave a gate open if we want to allow people to enter our property. So similar with our logic gates allow stuff to come in and they prevent stuff from coming in. And the stuff that they're preventing is actually a current, but we'll get to that later. Again, this video is just a high level overview of what we're going to be covering. So if there's things that you're not quite sure on, don't worry about it. We'll be going into detail in the next coming videos. So we can think of a gate as something that performs some operation or some function. So you can imagine this gate as a box, and when you put something into this box that it produces an output which is always the same. For example, when you put food into the microwave, it's cold, and then when you take it out, it's hot. So you don't know exactly what's going on inside the microwave, all you know is it heats up your food. So in a similar way, we can provide input to our gate. So the input that we could provide could be a binary number, so it could be 1 or 0. And it can take in not only one binary number, but many binary numbers. So we can just think of this as an input. And then we receive our output. And our output can be a binary number also. It can be 1 or 0. Now I would suggest, if you're not familiar with binary, to go and look at our binary videos before we jump into logic gates, because it can help you understand what's going on. But it's not a must. We'll be going through all in detail in this course anyway. So now we know that there's three different types of gates. There's a NOT gate, there's an OR gate, and there's an AND gate. And these different types of gates all do something different. We'll not worry about what they do yet. All we know is that they do something different. So for example, if I give an input, so let's say my input is maybe a binary number, so let's say it's 1 or 0, and I give my input to a NOT gate. So my NOT gate here will receive the input, it'll do some operation, so it'll change the data that I give it, and it'll give me some output, and the output it will give me will be a binary number as well, so it'll be a 1 or a 0. Now if I give that same input using a different gate, so if I was to use some binary numbers and use an OR gate, I would get a different output even though I gave the same input. I could give the exact same input to an AND gate but get a different outcome or a different output. So another thing you might be thinking of is, why do we need this? Why do we need logic gates, or why do we need these different type of logic gates? And the reason is by using multiple logic gates. So we usually don't use one logic gate by itself to do something. We usually use multiple logic gates. So we could use a NOT gate and an OR gate and an AND gate and maybe another OR gate. Or a simpler example might be us just using a NOT gate and an OR gate. And what this allows us to produce is a switch, or some people call it a flip-flop. And basically what it does, it allows us to change our bits. It allows us to flip our bits. So if you think of a real world example, like maybe in your room you have a light, you flick the switch on and off and your light either comes on or your light gets turned off. So to you, you know that switch will just switch your light on and switch that light off. But behind the scenes, there's a lot more going on. What's happening when your light is turned on and is in the on position, current or electricity is allowed to flow through the wire, and that produces the light that you see. Then when you hit that switch to turn the light off, that circuit is broken, so it's not a complete circuit, so it no longer lights the light bulb. So from this small example that I've drawn out, don't worry, you won't have to remember this. This is just to try and give you a better understanding of the previous example. So with anything we need a power supply. So to light up a bulb or an LED, we need some sort of power supply. So our power supply could be like a battery, so a battery that goes into your remote control, or a battery that goes into your car, or it could be a power supply like the electricity that's supplied to your house. So we've got a power supply. Now our current will run from positive to negative, so we're just going to draw in these little arrows to represent how the current is flowing. So you can see that the current is coming up, it's going across, it's going down, and it's meeting back up here, and this is completing a full circuit. And we can see we've got this little thing here. It looks like a triangle on its side with two arrows pointing out of it. This is just to represent LED, or we could have a bulb here or whatever. Just imagine this as a light. So when we've got this all connected together and we've got a complete circuit, our bulb will light up, or our LED will light up. Now, for whatever reason, if we wanted to stop this LED from lighting up, we would need to break the connection. So we would need to put a break in here, and then our LED would no longer light up. The problem is, if we then want to get our LED to light up again, we would need to rewire our circuit, or we would need to connect these two wires together somehow. Now that would be a pretty big problem if we had this in like a house or something like that. So this is where we have a switch. So a switch comes in, and a switch we can just place in here, and we can see that this switch is currently off. So we can see this circuit is no longer connected. But imagine that we move this switch and we connect it here. Now the current is allowed to flow. So our light bulb, or our LED, will light up again. Now, to take a deeper look at these switches, we use things called transistors. And I'm not going to get into it in too much detail because it's not really needed for this course, but I'm just going to draw a quick diagram. So if we look at this, we have our current over here on the left hand side, and our current is always flowing. So let's say it's always on. So the blue represents that current. Now we can see with our transistor here, our transistor will also have to be on for our circuit to complete. So if it's not on, then our current here will never be able to get this next wire here. And we can imagine that there's an LED out here that's going to light up. So if our transistor is off, which it currently is, we would not be able to light up our LED over here on the right hand side. But imagine we turn our transistor on. So we have our blue line, and now we have a current going up here, and we turn our transistor on. So now all that current is allowed to flow to this other wire on the right hand side, and now we can go and light up our LED or our bulb or whatever. So again, don't worry if you didn't understand everything in this video. What we're going to dive into in the next couple of videos will be our types of logic gates. That's what we're going to focus on mainly. So if you don't know about current or electricity or switches and things like that, don't worry about it. This video was just trying to give you a practical perspective of why these logic gates are used and how they're applicable. Hello everyone, in this video we're going to talk about NOT gates. Now in the previous video we discussed about gates in general and what they are and how they're used and why we need gates. So for this first video we're going to go through the NOT gate, and the reason why I've chosen the NOT gate over the other two gates is because the NOT gate is the simplest one to understand. So basically when you think of a NOT gate, just think of a process of doing the exact opposite of whatever the input is. So if I give you an example, if you take in a binary number, so a 1 or a 0, once that number is passed into a NOT gate, it will give the opposite as the output. So if we keep in mind from our previous video, we have an input. So our input will be 1 or 0, a binary number. Then after we've got our input, we'll have a process, and our process will just be a function that will manipulate our input in some way. And once our NOT gate has finished its function, it'll give us an output. And our output will be either a 1 or a 0, depending on what our input is. Now, when we get a circuit or a logical circuit, this will be made up of many different types of gates. So there could be a NOT gate along with an AND gate and an OR gate, or there could be a circuit that has multiple NOT gates and multiple AND gates. So it's quite important that we're able to familiarize ourselves with what these different types of gates look like. Now I know I went through it briefly in the previous video, but I'm just going to draw a diagram of what a NOT gate looks like. So this is what a NOT gate looks like. We have our input here represented by this line, and then this triangle with the circle, and then this triangle with the circle on top of it represents our NOT gate, and this line here represents our output. Now just keep in mind, with this type of gate, the NOT gate has only one input and one output. In some of the other gates that we'll be discussing, our AND gate and our OR gate, we can have multiple inputs. We'll still have one single output, but we can have multiple inputs. So for our demonstration videos, we'll be using 2 inputs for our OR gates and our AND gates. Now keep in mind, you can have more than 2 inputs for your OR gate and your AND gate, but for our NOT gate here, we're just using 1 input. So the next thing I want to introduce you to is the idea of a truth table. So a truth table is a simple table that you can draw with all the possible inputs for your NOT gate and the corresponding outputs or the results of them inputs. So I'll draw it out now and you'll be able to see. So you can see I've drawn out my truth table here. We have 2 values, we have an A and we have a B. A in this case represents our input and B represents our output. So as I said, a NOT gate takes in 1 value, so the only 2 possible values it could intake would be either 0 or 1. And when it takes in these values, it spits out the opposite. So the opposite of 0 is 1 and the opposite of 1 is 0. Now this might seem pretty simple. In the coming videos when we learn about OR gates and AND gates, they'll be a little bit more complex, but this video was just a nice introduction to the first type of logic gate that we use, and it also introduces us to the idea of our truth tables and our different symbols that we use to represent our gates. Hello everyone, in this video we're going to cover OR gates. Now in our previous video we covered NOT gates. They were quite simple. In this video our OR gates will be slightly more complicated, but you should be able to follow along. Now again, similar to the details I went through in our previous video, we have an input. So the only difference in this case, our input for an OR gate is slightly different than a NOT gate, because with a NOT gate we only have 1 single input, so it's either 1 or 0. While with OR gates we can have multiple inputs. So we could have an input which is 2 1s, so it's 1 1, or we could have an input that is 1 0, or we could have an input that's 0 0. So that would be any combination of 2 inputs. And we could also have an input that takes 3 values, or 4 values, or 5 or 6 or 7. But for this course we'll only be dealing with 2 input values, but you'll be able to see how 3 input values would also work. So first of all, just to show what our OR gate symbol looks like, you can see it looks like a little bit of a D misshapen or pushed to one side, or if we turn it sideways it looks a little bit like a spaceship. So in this example we can see our 2 lines here. So our 2 lines here represent our inputs. So if we had a 3rd input, we would have a 3rd line here, which would be whatever value that we're using. And you'll notice that similar to the NOT gate, we only still have 1 single output. So once we've done our function or our computation within our OR gate, we'll still only be producing one output. And I think the easiest way to think about this OR gate is to go and look at two binary numbers. So let's imagine two of our binary numbers. So the number 5 in binary is equal to 1, 0, 1. And we just put a 0 there at the beginning of it as well. You don't have to put a 0 if you don't want to. And then we're going to use an OR gate to get a result by ORing the number 5 and the number 1. So the number 1 in binary is 0, 0, 0, 1. So what we need to now do is we need to look at these different columns. So we can see that there's 4 different columns here. The first column has 1, 1 in it. The second column has 0, 0, and so on and so on. So with an OR gate, we are checking to see if one of these columns is 1. And if one of these columns is 1, we can bring down 1 to our next line. So with an OR gate, what we're doing is we're creating a new binary number. So we've got 5 and we've got 1 here as our input. And then once we've got 5 and 1 as our input, we're looking a little bit deeper and we're looking at 1, 1 here first of all. So we can see that 5 has got 1 and 1 has got 1. So as I said before, only one of them have to be true, or one of them have to be 1, and we can put a 1 down here. Now unfortunately, when we go to the next column, both of them are 0. So we have to put down a 0 here. And then when we look at the third column, we can see we've got 1, 1 and we've got 1, 0. So again, once we've got 1, we can bring it down because this is an OR gate. Now if it's an AND gate, it would be a little bit different. And again here we can see 2 zeros. So 2 zeros would give us an output of 0. And if you actually look at this number here, you'll see that this number here is equal to 5. So we're going to go and create a truth table to write down all the possible inputs and the solutions. So I've drawn out our truth table here. We can see that A will be our first input, B will be our second input, and Z will represent our output or our answer. So first of all, we need to come up with all the different combinations of 1s and 0s we can use with our OR gate. Now if you remember, to our NOT gate, we only had 2 different possible inputs because there was only 1 value that we took in as input. Now with this, we're taking in 2 inputs. So let's say the first example we could have is 0, 0. So both A and B could be 0. Our second possible inputs could be 1, 0. And another input could be 0, 1. And finally, our 2 inputs could be 1 and 1. Now, remember, with our OR gate, we're checking to see if one or both of our inputs are 1. If one of our inputs is 1, our output will be 1. Or if 2 of our inputs are 1, our output will also be 1. So the only problem we have is when our outputs are both 0. So we can see in this first example we have 2 zeros. So there's nothing we can do with that. Our output will be 0. Now moving on to the next input, 1 and 0 will be 1. 0 and 1 will also be 1. It's kind of similar to this one here. It's just that the values are switched. And for 1 and 1, our answer will be 1. And this is our truth table for an OR gate. Hello everyone, in this video we're going to cover AND gates. Now similar to our previous videos, if you've watched on our gates, we've covered a general overview of what gates are and how they work and why we need them and how they can be used. And then we moved on to learning about our NOT gate, and our NOT gate is our simplest form of gate. Whatever input it gets, it'll give us the opposite as our output. Then we moved on to OR gates, and with OR gates they were a little bit more complex than NOT gates because they could take in more than one input, so they could take in 2 inputs or more. Now with AND gates this is similar. So with an AND gate we can take in 2 inputs or we can take in 3 inputs or more. The only difference between an OR gate and a NOT gate is our truth table. So when we've got our inputs here, so our inputs could be 0, 0 or 1, 0 or 0, 1 or 1, 1. This is our input. When these inputs get pushed into our AND gate, the processing that our AND gate does will be slightly different than our OR gate, and therefore it'll give us a slightly different output. So if we go and jump into this, we can see that we will only get a true value, so we will only get 1 as our output if both of the inputs are true. So if 1, 1, we can see these are both true, so this will result in a 1 or a true value as an output. Now with these other inputs here, they're not both 1. So if it's any of the rest of them, unfortunately we'll get a false value, or as we represent it in binary, as 0. So if we go through our truth table here, we can see that 0, 0, again, both of these are 0. In an AND gate, we need both of them to be true. So we need both of them to be 1. So the result of this will be 0. So we can fill in 0 here. Then moving on to the next example, 1, 0. Again, they're not both 1, so this would be 0. Then moving on to the next one, again, they're not both 1. So it will be 0, and then finally our inputs 1, 1 will give us a result of 1. And this is our truth table completed for an AND gate. Now I want you to keep in mind, if there was more than 2 inputs, so imagine there was 3 inputs, imagine we had another input here which was C, so then we would have a totally different truth table. It would be quite a similar result, so only the values of A, B and C that were all 1 would give a true or 1 value as the result, and all the other values would be 0. So if we go and take a binary example that we can use our AND gate in, would be something like, if we picked a number, again we'll go with 5, similar to our OR, and we know that 5 in binary is represented as 1, 0, 1, and we'll pick 1 in this example, same as our last example, and we know 1 is represented by 0, 0, 0, 1. Now if you remember in our last video, when we computed this using an OR gate, we got our result as 5. Now you'll notice when we use an AND gate, we're going to get a slightly different result. So again, we're going to look at these two values here in this column, and we can see 1 and 1 will give us an output of 1, and we can see 0 and 0 will give us an output of 0. Now we can see in this we have a 1 and we have a 0. Now in our OR gate, all we needed was one of our values to be 1 to be able to bring down a 1 here to create our new binary number. Now unfortunately with an AND gate, again, both of the values have to be 1, so in this case this would be 0. So that's one difference between our OR gate and our AND gate. And then similar here, we have 2 zeros, so this will also be 0. And we can see this answer here is 1. Hello everyone, in this video we're going to be constructing a logic circuit. So we're going to use the type of gates that we've used in our previous videos. So we've learned about the OR gate, the AND gate and the NOT gate. So for this logical circuit example, we're going to be implementing all 3 different types of gates into one complete circuit. And then we're going to be given some values for our inputs into this circuit, and then it's our job to follow the input and output from each logic gate and come up with a solution so we can complete our truth table. So let's get started off by drawing our diagram. So we're going to get started off by drawing our first logic gate. You should recognize this type of gate. This is an OR gate, and with an OR gate we can see that we receive 2 inputs and we produce 1 output. So we can see with our next example here, we have a different type of logic gate, and this is a NOT gate, and we can see this by its symbol, along with, you'll notice there's only 1 input here for our NOT gate, and there's also going to be 1 output. Now we're going to bring both our NOT gate and our OR gate together and we're going to get these inputs and we're going to feed it into our final logic gate, which is an AND gate. And you should remember our AND gate always takes in 2 inputs, and again, similar to all the rest of our gates, it produces 1 single output. So this might be a simple question that's given to you. It would show you this logical circuit, and then it would give you some values for the inputs. So for example, for this input and this input and this input, and it would be up to you to step through the circuit and find out what the final output would be. So since we're dealing with binary numbers here, our inputs can only be 1 or 0 and our outputs can only be 1 or 0. So what we usually do is, when we're given a logical circuit like this, is that our inputs and outputs are all labelled. So keep in mind that these are our initial inputs and this is our final output, but this is also an output here and this is also an output, and these are inputs as well. So there's both inputs and outputs for our initial and final values, but there's also inputs and outputs that we can label inside our circuit. And especially if we're given a circuit that's more complex, it's useful to have these indications. So I'm just going to label this as A. So for my inputs here, these both will be the same, so whatever value we're going to assign to A. Then moving on to our next input, we'll call this one B, so we'll assign some input for B. And just stepping through the rest of the program, we're going to call this C, so this is technically the output of this OR operator and the input of this AND operator. These will be the same value, and the same for this. The output of this NOT gate will be the input of this AND gate, and we'll call this D. And then for our final output and our result for this example, we'll call it E. So I've created my truth table here, and we can see we have 5 different values, A, B, C, D and E, and for us to start our calculations we need to have an input for A and B. So when we're given this truth table in an exam format or something like that, we'll be given some of these values initially. So for example, we might be given A's input value and B. So for example, we might be given the value 0 for A and the value 0 for B, which would mean we start off here with our 2 inputs being 0 and 0, and then for B our input is also going to be 0. And from this we can figure out the other 3 values. So let's just step through this, and I'm actually going to use a different colour for my input and output values just to make it a little bit more readable. As we said before, A's value is 0, so we're going to put 0 and 0 for our 2 inputs of A, and we're also going to have 0 for B because our value is 0 for B also. Now when we go through our NOT gate, we know that our NOT gate flips our bit, right? So whatever our input is, it gives us the exact opposite. So we know if we get a 0 in here, we're going to get a 1 as our output. If we had a 1 here, we would get a 0 as our output. So beside D here, I'm just going to put 1 because that's the value that we're going to have. And our OR gate here will be true, or will be 1, if 1 or more of the values are 1. Now unfortunately for this example, both of our input values here are 0, so 0 and 0 still gives us our output as 0 or false. So I'm going to put down 0 beside C because that's the value for C. Now moving on to this next step, you can actually bring this 0 down here if it makes it a little bit more readable for you, and we can bring this 1 here. And now we can say we're entering an AND gate. So for this outcome here, E, to be true or 1, both of the values have to be 1. So as you can see in this example, one of the values is 0. So unfortunately for E, we'll get our output as 0. And then if we go and fill in this table, so let's say for example for C our value is 0, for D our value is 1, and for E our value is also 0. So I'm going to move on to another example. Let's say this time our input for A will be 0 and our input for B will be 1. So we put 0 down for A and we put 1 down for B. Now again I'm going to switch to a different colour pen just for readability. So the same as last time, we've got A as 0 and our B value is 1 this time. So when we pass this through the NOT gate, we'll see when we flip 1 it becomes a 0, so D becomes a 0. With our OR gate, both of our values are still 0, so C will also be 0. We can bring this down here if we want, but by looking at this, 0 and 0 passed through an AND gate will give us our output as 0. So to fill this in, we can see that C is 0, that D is 0, and E is 0. So this time we're going to use the exact same inputs for A and B, and you might be wondering why. You might think that would we not get the exact same outputs, and we would, but there's going to be one small little change that we're going to make. So do you see this bridge here? This is basically allowing B to be the input into this OR gate rather than A. So for this next example, this second input for this OR gate will actually be 1, because we can see B here is 1. So we're going to put 1 here just to identify it, and B is going to be 1. Now this is actually going to change things a little bit. So when B is passed through this NOT gate, again, this is going to become a 0. Now when we pass a 0 and a 1 through an OR gate, only one of them have to be true, so C in this case will actually be 1, while in the last scenario it was 0. But then again, when we go and try and put a 0 and a 1 through an AND gate, it will end up being 0. So the difference between this is C here is a 1 rather than a 0, but D and E still stay the same. So the next two examples that I'm going to do will be 1 and 0 and 1 and 1. Now I suggest you go and try and see can you do these by yourself, and if not, no worries, just keep in mind that this time we're going to also use B as our second input for this OR gate, because we're going to take advantage of this connected circuit here. So if you're unsure what to do, or you've attempted the question, I'm going to go through the answer now. So for A, as we can see here, we're getting a 1, and for B we're getting a 0, so this will be 0 because remember B is linking up this time, and this B will also be 0. So when 0 is passed through a NOT gate, D becomes 1. Now when we pass this through to C, we know that only one of these values have to be 1 for our output to be 1, so we can say C is 1. So when 1 and 1 is passed through an AND gate, we get a 1 as our answer, so E is indeed equal to 1. So our truth table for this solution would look like this: C is 1, D is 1, and E is 1. So for our last and final example, we have our inputs for A and B as both 1, so this will be 1, this will be 1, and this will be 1. Now when 1 is passed through our NOT gate, our D becomes 0. When we pass 1 and 1 through an OR gate, only one of them have to be true, but two of them can also be true, and it will give us an output as 1. Now when we put a 1 and a 0 through our AND gate, both of these values are not 1, so our output will be 0. So to fill in our truth table, C will be 1, D will be 0, and E will be 0.